All right. Let's talk about section 2.3, tangent lines revisited. Okay, recall, as you guys have been shown before, given a function, a tangent line to that function is a line that only passes through one point and one point only, like so. So given a function f of x in the blue, a tangent line at some point A, f of A, is a line that passes through that point of the function at A, comma f of A. Okay, so then we figured out, oh, if this is f of x, then f prime of x evaluated at various points gives us slope values for these lines. And whenever we know the slope values, we can construct a tangent line because we can use point slope form. Y minus y1 is equal to m times x minus x1. Okay, so theoretically, we can actually, given any function whose derivative we can take, we can evaluate it at any point f of a, find out what the slope is, then pick that point, stick it in the point slope form, and construct a equation for the tangent line. Okay, so for example, let's take this function, 7x cubed minus 4x squared plus 1 at x is equal to 1. All right, y prime of x is then 3 times 7 is 21. Put x squared here, minus 2 times 4 is 8. Derivative of a constant is 0, so this is what we get here. So if we want to know x equals 1, we want to see what y prime of 1 is. That's 21 times 1 squared minus 8. That's 21 minus 8. And this decomposes down to the value of 13. So the value of 13 is our slope m. Construct a tangent line requires y minus y1 is equal to m times x minus x1. And we need a coordinate pair, x1 and y1. We can find that point because x equals 1 implies f, or let's say y of 1, is 7, 1 cubed minus 4 times 1 squared plus 1. So y of 1 is equal to 7 minus a 4 plus a 1. So this ends up becoming a 5. What am I saying? I mean a 4. Okay. So a point 1 comma y of 1, which is our x1 comma y1, ends up becoming 1 comma 4. So then we can plug those values into here, and we get y minus y1 is equal to m. We've discovered that's 13 times x minus x1. So this becomes 13x minus 13. And that implies we got y is equal to 13x minus 13 plus a 4. And that equals 13x minus a 9 is equal to y of x. Or what we call t of x. Actually, we can call this t of x to be the tangent line of x. Let's do another example. We have x cubed minus 2x plus pi is equal to our f of x. Let's do the same thing for x equals negative 1. Well, f prime of x is 3x squared minus 2. And so the slope at x equals 1 is evaluating the derivative. So this is 3 times 1 squared minus 2. That's 3 minus 2, which is 1. This is our slope. Okay, and f of 1 is 1 cubed minus 2 times 1 plus a pi. So this becomes 1 minus 2 plus a pi. So this becomes pi minus a 1, which is our f of 1. So our coordinate pair is 1 comma pi minus 1. That implies y minus y1 is equal to m times x minus x1. So that implies we got y minus our y1, which is pi minus 1, is equal to our slope 1 times x minus 1. So that implies we get y minus a pi plus a 1 when you distribute a negative into here. Is equal to x minus 1. That implies y is equal to, when I subtract the 2 from both sides, I get a minus 2. When I add a pi, I get a plus a pi. And this x stays here. So this is our equation. Okay. Now, let's talk about finding horizontal tangents. A horizontal tangent. So recall we have some function and we have a tangent line. We notice the tangent line is flat at a peak or a trough of the function. Boom. Not a very tangenty tangent line, but you know, you got to work with me here. So notice that those lines are horizontal if I drew them right. This means that at this point, if this is f of x, here f prime of x, which is your slope, has value 0. F prime of x, which is your slope, has value 0. So we can find all of these values of a function if we find its derivative and set it equal to 0. So for example, what about f of x is equal to x squared? This is our beloved parabola. Okay. Clearly, we see that there's going to be a horizontal tangent here. But let's discover that mathematically and not just rely on the visual. Let's actually discover it. Notice that f prime of x is equal to 2x. All right. So now we can actually, we took the derivative. Now let's set it equal to 0. Let's find all of the values in which makes this equation equal to 0. Well, dividing both sides by 2, I get x is equal to 0. So, aha, we visually and algebraically see that that's where we might get a horizontal tangent. Not might, definitely. It's 100% certain we'll get there. But let's do something more complicated, okay? What about f of x is equal to x to the 13th minus x, all right? Where does this guy have horizontal tangents? Well, we can take its derivative, f prime of x, and that's 13x to the 12 minus 1. Notice that we could set this equal to 0 to discover where the points of horizontal tangents are. So that's 13x to the 12 is equal to 1. Divide both sides by 13, we get x to the 12 is equal to 1 over 13. And then we could take the 12th root of both sides. So we get x is equal to the 12th root of 1 over 13. Okay? And since this is an even root, it's technically plus or minus. So technically, when we keep going, this is plus or minus 1 over the 12th root of 13. And you can rationalize the denominator, so you get plus or minus the 12th root of 13 all over 13. These are the values in which this function is going to have horizontal tangents. Right now, this doesn't really. Right now, it doesn't really seem why we're interested in these values. But if you look at the function here in general, if this function were to like represent how much a stock's value is or how fast something is going, these horizontal tangents will actually measure when is the maximum and when is the minimum of whatever this function is trying to quantify. So the extreme values, maximum and minimum values, will be quantifiable via setting the derivative equal to 0. So it allows you to find maximum and minimum values, which is important information. So in application, that's why what we're doing is important. So let's do f versus f prime. Here's an example. We have f of x is equal to x squared plus 1. Let's graph it. It's a parabola that's been vertically shifted by 1. Okay. So what is f prime of x? Well, that's just 2x. What does that look like? Oh, that's a line of positive slope where the slope is equal to, you guessed it, 2. And it has a y-intercept of 0. And that's why it's going through the origin. So this is f, and this is f prime. Let's juxtapose these two values. This is the function, and this is its derivative. What do we notice here? Oh, well, we notice that horizontal tangent lines of the function correspond to horizontal tangent lines of the normal function correspond to the derivative function going through the x-axis. Right now it's going through the origin, but if we had shifted this like so, let's say we have this function where in the blue, I've horizontally shifted this to the right. So f of x ends up equaling, it's x minus 1, because it's a shift to the right, quantity squared, and it's shifted up, so 1. So f of x is equal to the quantity x minus 1 squared plus 1. This is a horizontal shift to the right. This is a vertical shift up. That's our function right here. This is at 1, 1. This is at 1, 1. That's where the graphs, the parabola's vertex is. We'll notice that that's exactly where we're going to find this horizontal tangent when we do this mathematics. So f prime of x is equal to, let's take the derivative of this guy. Okay, let's see here. Notice that this is dx of this right here. Notice that's dx of x minus 1 times x minus 1 plus 0, because ddx of a constant is 0. Okay. Notice that ddx of a product of two functions, f times g, recall that's f prime g plus g prime f. So that's, we can call this f and we can call this g. So then that means the derivative of f is just a 1 times g, which is x minus 1, plus the derivative of g is just a 1 times x minus 1. So we end up getting 2x minus 1. Okay. So then this is our derivative. And we can set it equal to 0. That means we got 2 times this x minus 1 equal to 0. Divide both sides by 2. We get x minus 1 is equal to 0. That implies x is equal to 1. Boom. So that gives us this part. But what about this part? well, then we can evaluate the function f of 1, and that's this x that ends up becoming 1 minus 1 quantity squared plus 1, which is 0 plus 1, which is 1. So 1 comma f of 1 is equal to 1, 1, precisely what we'd expect over here. Okay? So now, given f of x, sketch the graph of f prime of x. And doing this is actually, it seems difficult, but it's not that bad. So let's be given a function like so. These are f of x. Let's say this is some point A. This is some point B. Actually, I want to call this point A right here. All right. And this point B. And I want to call them that because there's a horizontal tangent here and a horizontal tangent here. So we know that at A, f of A, and at B, f of B, that there's a horizontal tangent. Okay, but then we notice that, okay, the slope here is negative. Over here it's positive. And over here it's negative. And so that means if I were to graph f prime of x, that over here to the left of A, its slope value was negative. So it's going to be negative. But when it reaches A itself, the slope becomes 0. So if f prime of x quantifies the slope values, it's going to be negative and then cross the x-axis at A. Then beyond A, all the way to B, it's positive. And at B, it becomes 0 again. So it goes to the positive and then it becomes 0 at B again. Surpassing B to higher values, we notice that the slope is negative, so it goes down again. All right. So this is f prime of x right here. And we were able to sketch it based off of analysis of the normal function, f of x. Okay. Let's talk about local linearity. Recall that said, well, f of x plus some alpha may be approximated as f of x plus alpha times f prime of x. Okay, that's local linearity algebraically. This is what it is graphically. Say you have a function like this, and we look at this part, we zoom into it, and we notice it looks like this. Okay, but then we zoom into this part again, and we notice that once we zoomed in, this looks pretty curvy, but once we zoom in a second time, it starts to look pretty straight. And if we zoomed in again, it's indistinguishable from a straight line. So local linearity says that locally, when you zoom in far enough into a graph that is differentiable and continuous, although recall that differentiable implies continuous, but continuous does not imply differentiable. So if it's differentiable, that means it is continuous. So if it's a function that's differentiable, then local linearity applies. That means if we zoom in to any point, that eventually it looks like a straight line. The graph will eventually be infinitely approximate. It can infinitely be approximated as just a straight line locally, not globally, but locally. Globally means when we zoom out. All right. So what this entails, is, I'll tell you in 1 second. So let's draw a generalized graph, if you will. And we can do this by saying, okay, let's have some arbitrary function f of x. And let's have a tangent line. Like so. Then if we do that, we can build some dx and some dy. Dx and dy just means a small piece of x and a small piece of y. A differential piece, if you will. Okay? We bring this down and call this k. And call this k plus some dx. Then that means that this value right here is some f of k. And all the way up here is f of k plus a dx. So we notice that this height is our delta y, but that this height is the dy. Notice that delta y is strictly greater than or equal to dy. Okay? But notice as we zoom in, if we keep zooming in and keep zooming in and keep zooming in, this by local linearity will give us that delta y is indeed just some dy. Okay? It can be approximated to be like that. So that means delta y is equal to f of k plus dx minus f of k. Just from saying that this is delta y, we'll take those two values and subtract them from each other. Okay. And another fact that we can extract here is that f prime of k is equal to the ratio dy over dx. Because it's rise over run. Because that's equal to our slope. So f prime of k, by definition, is f of k plus alpha minus f of k all over alpha. We notice that this ends up equaling delta y over alpha. And dx can actually infinitely approach an infinitesimal value. So as that happens, this is what we get. Delta y over dx. But by local linearity, we get this. So, aha, the derivative of the function evaluated at k is the ratio dy dx if we zoom in far enough. If we zoom in far enough, this gap becomes insignificant. That's what we're saying here. This gap right here between this point and this point, that goes to 0. And so really the function is dy over dx, its derivative value. Dy dx is now synonymous with f prime of x. And dy dx evaluated at x equals k is synonymous with f prime of k. Okay, so now this means we can do something, we can do a process called linearization. This means we locally approximate a function with a line. Okay, here is an example. All right, let's say you have a function f of x. You have a point a, f of a on this function. you can find in f prime of a, which is equal to your m. Then you can say y minus y1 is equal to m times x minus x1. Notice that's y minus f of a, which is equal to our m, which is f prime of a, times the quantity x minus a. Notice that when we do the algebra, this is what we get. So we get y is equal to f of a plus f prime of a x minus f prime of a. But notice we can then say, oh, well, the y is just equal to f of a. We factor out that f prime. We get that. We say that that is the linearization of our function f of x. So the linearization of f of x, L of x, is precisely this f of a plus f prime of a times the quantity x minus a. This is what we would call the linearization of f of x near x equals a. So near the value x equals a, we can create a linearization of the function f of x. The function may not be a linear function. It could be very curvy and squiggly, but near the point x equals a and slightly to the left and slightly to the right of x equals a, we can approximate it using that function, the linearization. So how do we apply this to a real life situation? Let's take a function f of x is equal to the square root of x. At x equals 4, find the linearization. Okay, so recall the linearization of x is equal to f of a plus f prime of a times the quantity x minus a. All right, a is 4, so f of 4 is square root of 4, which is 2. F prime of 4 is equal to d dx of, let's just say f prime of x for now, d dx of square root of x, and that's d dx of x to the 1/2 power. So that's 1/2 x to the negative 1/2. This is our f prime of x. So then f prime of 4 is equal to 1/2 times x times 4 raised to the negative 1/2. So that's 1 over 2 times the square root of 4, and that's equal to 1 over 2 times 2. So that's 1 over 4. This is our f prime of 4. So we have all the ingredients we need to calculate the linearization. So the linearization of x is equal to f of a, which is f of 4, which is 2, plus f prime of a, which is f prime of 2, which is f prime of 4, which is 1 over 4, times x minus a, which is x minus 4. So this becomes 2, we're actually done here. Okay, we found the linearization. So now, once we find the linearization, use the linearization to approximate what is f of 4.01, for example. Well, why did I pick 4.01? That's just like a value slightly different than 4, a little to the right of 4. And the linearization is only accurate for values very close to that x equals 4. So the linearization is an approximation. So f of 4.01 is approximately equal to L of 4.01. And it's a valid approximation because the linearization is only valid for very close values above and below the value x equals 4. So then this becomes 2 plus 1 over 4 times 4.01 minus 4. So this becomes 2 plus 1 over 4 times 0.01. So this becomes 2 plus 1 over 4. 0.01 is like 1 over 100. So this is like 2 plus 1 over 400. So this is like 800 plus 1 all over 400, which is equal to 800 and 1 over 400. And 800 and 1 over 400 approximates to, that should be approximately 2, right? Because 400 can go into 800 twice. So 400 can go into 801 a little bit over 2, very slightly over 2. But there we have it. We were able to approximate our function at a value slightly to the right of x equals 4. And in this problem, it may seem trivial, but for very complicated polynomial functions, it actually becomes invaluable. Okay?